Hello, friend. Welcome back to another quiet journey through the cosmos. Some nights when the world finally falls silent, you might find yourself staring up at the sky, stars scattered like salt across black velvet, distant, unreachable, beautiful in a way that makes you feel small. But here's what's strange: the universe isn't just vast, it's puzzling. Out there beyond the glow of streetlights and the hum of daily life, mysteries drift through the dark. Things science can't yet explain. Phenomena that shouldn't exist, yet they do. And tonight, in the quiet of this moment, we're going to explore them together. Before we begin drifting through these cosmic riddles, if you find comfort in these gentle explorations of the unknown, you might like to stay a while. You can softly tap the like button, subscribe, if these quiet science stories feel like home, and ring the little bell not for noise, but so the next starlit journey can find you again when you need it most. Now, let's drift. Tonight we'll move slowly through 8 of the universe's deepest mysteries. Not to solve them, some questions are more beautiful, left open, but to feel them. To let wonder do what wonder does best: remind us how much we don't know, and how thrilling that can be. You don't need to understand everything. Just rest your thoughts and let curiosity lead the way. The universe began with a whisper, scientists suggest. 13.8 billion years ago, everything we know burst from a point smaller than the period at the end of this sentence. Space expanded, time began. Matter cooled into atoms, atoms into stars, stars into galaxies. And now, billions of years later, here we are, creatures made of stardust, looking back at the sky that made us asking what else is out there. It's a question older than telescopes. Ancient humans stared at the same stars we see tonight, crafting stories to explain the lights above. The Greeks saw gods. The Mayans tracked Venus with stunning accuracy. The Polynesians navigated oceans by reading stellar patterns like maps written in light. They knew the sky held secrets. They just didn't know how deep those secrets went. When Galileo first pointed his telescope toward Jupiter in 1610, he saw something no human had ever witnessed: 4 moons circling. Not everything revolved around Earth. The cosmos was larger, stranger than anyone imagined. And with each century, each new lens we turned skyward, the universe revealed not answers, but better questions. In 1929, Edwin Hubble discovered something unsettling. Galaxies weren't standing still. They were rushing away from us, from each other, like guests fleeing a party that never ends. The universe was expanding, which meant that once long ago, it had been smaller, denser, hotter. This realization gave birth to the Big Bang Theory, a name that sounds explosive, but the truth is softer. It wasn't a bang, it was an unfolding, a breath. And here's where it gets strange. The more we learn, the more we realize most of the universe is invisible, not hidden behind clouds or curtains, but fundamentally unseeable. Dark matter, dark energy, terms that sound like placeholders because in a way they are. We know they're there because of what they do, not what they are. Galaxies spin too fast to hold together with the gravity from visible matter alone. Something unseen is stitching the cosmos together. We've named it, mapped its effects, but we've never touched it, never seen it directly. It's like knowing someone lives in a house because the lights turn on at night, but you've never glimpsed their face. Some scientists spend entire careers chasing particles that might not exist. Detectors buried miles underground wait in silence, hoping for a whisper of interaction. A dark matter particle colliding with ordinary matter just once. It hasn't happened yet, but they keep waiting, because what else is science but organized patience? Then there are the signals. In 1977, a radio telescope in Ohio picked up a transmission from space so strong, so unexpected, that the astronomer monitoring the data scribbled "wow" in the margins. The signal lasted 72 seconds. It never repeated. For over 40 years, we've listened to that same patch of sky, hoping it would speak again. Silence. Was it a natural burst from a distant star? A fluke in the equipment? Or something else, something we're not ready to name? Do you ever wonder if we're alone? It's a question that feels too big to ask out loud, yet it sits quietly in the back of the mind. Statistically, the universe should be teeming with life. Billions of galaxies each, with billions of stars, many with planets in the habitable zone, where water could pool and chemistry could complexify into something alive. The math suggests we should see them, hear them detect some ripple of their existence. But we don't. The skies are silent. This is the Fermi paradox, named after physicist Enrico Fermi, who once asked at lunch, "Where is everybody?" Maybe intelligence is rare. Maybe civilizations rise and fall before they can reach out. Maybe they're out there watching, choosing silence. Or maybe we're the first, the only ones awake in a universe still learning to dream. Either possibility is staggering, and space doesn't just hide in distance, it hides in time. Light from distant stars takes so long to reach us that we're always looking backward. When you gaze at Andromeda, our neighboring galaxy, you're seeing it as it was 2.5 million years ago. If someone in Andromeda looked back at Earth right now, they'd see our planet as it was before humans walked upright. We're all ghosts to each other, separated not by space alone, but by time's cruel geometry. Einstein showed us that time itself isn't constant. It bends, stretches. Near a black hole, time slows so dramatically that if you could hover just beyond the event horizon and watch the universe, you'd see stars born and die in what felt like moments. An hour there could be decades elsewhere. Time becomes negotiable, flexible, strange. This isn't philosophy. This is physics tested and confirmed by atomic clocks, flown on airplanes by GPS satellites, adjusting their signals to account for the warping of space-time. Even the fabric of space itself is peculiar. Quantum mechanics tells us that at the smallest scales, particles blink in and out of existence. Empty space isn't empty. It seethes with virtual particles flickering for fractions of a second before vanishing. The vacuum hums with potential. And sometimes two particles born together remain connected no matter how far apart they drift. Change one and the other responds instantly even across galaxies. Einstein called it spooky action at a distance. He didn't like it, but experiments have proven it true. The universe, it seems, remembers connections even when distance tries to erase them. We've built machines to listen to the cosmos, radio telescopes the size of cities, scanning frequencies, filtering noise, hoping for a pattern that isn't random. We've sent messages into the void, golden records on Voyager carrying music, greetings diagrams of hydrogen atoms, a message in a bottle flung into an ocean we'll never cross. Will anyone find it? Probably not, but we sent it anyway. Because hope, like curiosity, doesn't require evidence. It just requires breath. And that's the thing about mysteries. They don't diminish us, they expand us. Every unanswered question is an invitation. Every anomaly is a reminder that the universe still has stories to tell, and we're still learning the language. So, tonight we'll walk gently through some of those stories. We'll visit the great silence where we wonder why no one answers. We'll touch the invisible skeleton of dark matter holding galaxies together. We'll listen to fast radio bursts, signals from depths we can barely fathom. We'll examine strange visitors like Oumuamua objects that pass through our solar system, like travelers who never stop to say hello. We'll study the faint afterglow of creation itself and find cracks in its perfection. We'll explore quantum entanglement, where distance loses meaning. And we'll stand at the edge of black holes, where time forgets how to tick. None of this will give you answers, but it might give you something better: wonder, the kind that makes sleep feel like floating, the kind that reminds you that being small in a vast universe doesn't mean being insignificant. It means being part of something too large, too strange, too beautiful to fully comprehend. And maybe that's enough. The sky is full of whispers. Let's listen for a while. Our first mystery is one of absence, of silence, of a question so profound that entire branches of science have formed just to contemplate it. It's the riddle of loneliness on a cosmic scale. Imagine throwing a party and no one shows up. Now imagine that party is the entire universe, and you've been waiting for 4.5 billion years. In 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory. The conversation wandered as lunch conversations do, from recent UFO reports in the newspapers to the possibilities of faster-than-light travel. Then Fermi went quiet for a moment. When he spoke again, it was with a simple question that would echo through decades: where is everybody? His colleagues knew exactly what he meant. The universe is ancient, vast beyond comprehension. Our galaxy alone holds somewhere between 100 and 400 billion stars. Many of those stars have planets. Many of those planets sit in zones where liquid water could exist. The chemistry of life, as we understand it, isn't exotic. Carbon, hydrogen, nitrogen, oxygen, these elements flood the cosmos. Given enough time, given the right conditions, life seems almost inevitable. And if life, then perhaps intelligence. And if intelligence, then technology. And if technology, then signals, we could detect structures, we could observe some ripple of presence across the electromagnetic spectrum. But when we listen, we hear nothing. When we look, we see no one. The silence is so profound it has a name: the Fermi paradox. Not truly a paradox in the mathematical sense, but a tension between expectation and reality. We should see them. We don't. Why scientists suggest several possibilities, each more unsettling than the last. One idea holds that intelligent life is staggeringly rare, that the leap from chemistry to biology, from single cells to complex organisms, from awareness to technology. Building civilizations might involve so many unlikely steps that even in a universe this large, we could be one of the first, perhaps even the only ones. It's called the rare Earth hypothesis, and it suggests that Earth isn't typical, it's a cosmic lottery winner. Our moon stabilizes our axis. Our position in the galaxy avoids radiation-heavy zones. Jupiter's gravity shields us from excessive asteroid impacts. The list of coincidences grows long enough to make you wonder if we're not just rare, but unreasonably lucky. Then there's the Great Filter. This concept, proposed by economist Robin Hanson, suggests that at some point between lifeless chemistry and galaxy-spanning civilizations, there exists a barrier, a filter so difficult to pass that almost no one makes it through. The terrifying question becomes, is the filter behind us or ahead of us? If behind us, then we're among the few who've crossed it and the universe lies open. If ahead, then every civilization that has ever arisen faces an insurmountable wall: nuclear war, climate collapse, artificial intelligence gone awry. Perhaps intelligence itself carries the seeds of self-destruction. And the louder you broadcast your presence, the closer you get to silence. Have you ever considered that loneliness might not be an accident, but a choice? The zoo hypothesis proposes exactly this. Perhaps advanced civilizations exist, but they have agreed not to contact us. We're being observed, studied the way researchers watch animals in a nature preserved close enough to document, careful not to interfere. If true, then first contact wouldn't happen until we reach some threshold of development, some marker that proves we're ready. What that marker might be, no one knows. The ability to travel between stars, the resolution of war. Something subtler, something in how we treat each other or our world. Or maybe they're quiet because speaking is dangerous. The dark forest theory, popularized in science fiction, but rooted in game theory, suggests that any civilization capable of interstellar communication must weigh a terrible risk. Revealing yourself to an unknown cosmos could invite destruction. If you don't know whether the voice in the dark is friend or predator, silence becomes survival. Every civilization crouches in the undergrowth, listening, afraid to light a fire that might be seen. The universe becomes a dark forest full of hunters who dare not breathe too loud. In 1961, astronomer Frank Drake developed an equation to estimate the number of detectable civilizations in our galaxy. It wasn't meant to provide an answer, the variables were too uncertain. but to frame the question properly. You multiply factors, the rate of star formation, the fraction of stars, with planets, the number of planets that could support life, the fraction where life actually arises, the fraction where intelligence develops, the fraction that builds detectable technology, and finally, the length of time such civilizations broadcast signals into space. Plug optimistic numbers into Drake's equation, and you get thousands of civilizations we should be able to detect. Use conservative estimates, and you might get one use. The equation doesn't solve the mystery, it maps its dimensions. And depending on which assumptions you trust, the answer swings from cosmic loneliness to a galaxy crowded with neighbors who simply haven't introduced themselves yet. We've been listening for over 60 years. In 1960, astronomer Frank Drake aimed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals that might indicate intelligent origin. This was Project Ozma, the first systematic search for extraterrestrial intelligence. He found nothing, but he'd opened a door. Now, programs like SETI, the search for extraterrestrial intelligence, scan millions of frequencies filtering cosmic static for patterns that nature wouldn't make on its own. The challenge is enormous. Radio waves travel at the speed of light, and space is relentlessly big. A signal from a civilization 1,000 light years away wouldn't reach us for 1,000 years. And that's assuming they're broadcasting in a direction we can detect, at a frequency we're monitoring using technology we'd recognize as communication. We could be two ships passing in a night, too dark to see each other's lights. Some scientists believe the era of radio broadcasting might be brief in a civilization's timeline. We've been radiating television and radio signals into space for less than a century. Already we're shifting to fiber optic satellite systems that beam signals toward Earth rather than outward. If other civilizations follow a similar path, their radio window, the period when they're loud enough to detect, might last only a few hundred years. In a galaxy billions of years old, that's a blink. We could be listening during the wrong century, looking for a technology they've already outgrown. Then there's the possibility we're searching incorrectly. We assume intelligence would communicate the way we do through electromagnetic radiation, encoded information, deliberate broadcasts. But what if advanced civilizations use methods we haven't conceived? Gravitational waves, quantum entanglement, something woven into the structure of space-time itself. We might be like someone in the 1800s searching for telegraph signals while others communicate via internet. The message could be passing through us unnoticed because we don't yet know what listening means. There's also the uncomfortable thought that intelligence might not survive long. Research shows that species on Earth typically last a few million years before going extinct. Homo sapiens has existed for roughly 300,000 years at cosmic eye blink. If technological civilizations follow similar patterns, the window for contact becomes vanishingly small. Two civilizations need to exist simultaneously, develop detectable technology simultaneously, and be looking in each other's direction simultaneously. The odds shrink with each requirement. Still, we keep searching. The Breakthrough Listen project, funded by billionaire Yuri Milner, surveys 1 million stars for signs of artificial signals. The Allen Telescope Array in California scans the sky continuously. China's FAST telescope, 500 meters in diameter, listens with unprecedented sensitivity. We've sent messages too. The Arecibo message in 1974, a radio signal aimed at the globular cluster M13, encoded with information about humanity, our biology, our solar system. It won't arrive for another 25,000 years. Even if someone receives it and responds immediately, we won't hear back for 50,000 years total. The conversation moves at the pace of geology. Some argue we shouldn't broadcast at all. Stephen Hawking warned that advertising our presence could be catastrophic. If aliens visit us, he said, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. History teaches that when a technologically advanced civilization meets a less advanced one, the encounter rarely favors the latter. Silence in this view isn't loneliness, it's wisdom. But others counter that remaining quiet changes nothing. Our television broadcasts have already rippled outward for decades, a sphere of radio noise expanding at light speed. Any civilization close enough and advanced enough to be a threat would already know we're here. Hiding now would be like whispering after shouting. So we wait, we listen, we wonder if perhaps we're asking the wrong question. Maybe the Fermi paradox isn't about where everyone is, but when. Civilizations rise and fall. Perhaps the galaxy has been full of voices, just never at the same time. We're singing into a cosmos that once rang with songs now silent, waiting for the next verse. Or perhaps intelligence isn't the pinnacle we imagine. Life has thrived on Earth for billions of years without technology. Bacteria, fungi, plants, they have outlasted every advanced species that ever walked. Maybe consciousness and tool building are evolutionary dead ends, beautiful but brief experiments. Maybe the universe favors simplicity and intelligence burns too bright to last. There's strange comfort in not knowing. If we found a signal tomorrow, a clear, undeniable message from the stars, everything would change. We'd know we're not alone, but we'd also face the weight of comparison. Are they peaceful, hostile, indifferent? Would contact elevate us or diminish us? The uncertainty lets us dream. And yet, the silence teaches something too. It suggests that if we're not alone, we're at least rare enough that our existence matters. That consciousness, wherever it arises, is precious. That this small blue world, with its 7 billion voices, might be something extraordinary. The universe doesn't owe us neighbors. It doesn't owe us answers. What we have this moment, this awareness, this ability to ask where everyone is, might be rarer than we'd like to believe. So we keep building better telescopes, keep refining our equations, keep sending signals into the dark hoping for an echo. Not because we expect results, but because the search itself is an act of hope. It says we believe in possibility, that we're willing to look beyond ourselves and imagine kinship with minds we've never met. The great silence isn't empty. It's full of potential. Every star could be a sun to someone. Every quiet frequency could carry a message we haven't learned to hear yet. And in the meantime, as we listen to the cosmos and hear only our own breath echoing back, we're reminded of something fundamental: we have each other. For now, on this small world, we're the universe's way of knowing itself. And maybe that's enough. Maybe that's everything. But silence isn't the only mystery the universe keeps. Beyond the question of presence lies the riddle of substance of matter we cannot see but know is there. Picture this. You're living in a house where most of the furniture is invisible. You can't see the chairs, the tables, the walls holding up the ceiling. But you know they're there because when you reach out, you feel resistance. When you walk, you navigate around shapes you cannot perceive. Everything functions as it should, held together by structures your eyes refuse to acknowledge. That's our universe. And the invisible furniture, we call it dark matter. In the 1970s, astronomer Vera Rubin did something simple that changed everything. She measured how fast stars orbit around the centers of galaxies. According to the physics, we understood Newton's laws carefully refined over centuries. Stars farther from a galaxy's core should move slower, just as planets farther from the sun take longer to complete their orbits. Mercury races, Neptune crawls. The math is clean, predictable, confirmed by every observation we'd ever made in our solar system. But Rubin found something impossible. Stars at the outer edges of galaxies were moving just as fast as stars near the center. Some were moving faster than they should, far faster. So fast, in fact, that galaxies should be tearing themselves apart, flinging stars into intergalactic space like water droplets off a spinning wheel. Yet, they weren't. Galaxies held together, serene and stable, as if gripped by invisible hands. Rubin wasn't the first to notice the discrepancy. In 1933, Swiss astronomer Fritz Zwicky observed galaxy clusters and calculated their mass based on how bright they appeared. Then he measured their mass based on how they moved, how gravity seemed to be pulling on them. The two numbers didn't match, not even close. The gravitational mass was hundreds of times larger than the visible mass. Zwicky proposed that most of the matter in these clusters must be dark present but unseen. His colleagues largely ignored him. The idea seemed too strange, too inconvenient. But Rubin's work was harder to dismiss. She studied galaxy after galaxy, and the pattern held. Rotation curves graphs showing orbital speed versus distance from the galactic center stayed flat when they should have dropped. The evidence was mounting. Either our understanding of gravity was fundamentally wrong, or the universe contained vast quantities of matter we couldn't see. Scientists suggest that roughly 85% of the matter in the universe is this dark matter. Not dark because it's shadowy or hidden behind clouds, but dark because it doesn't interact with light at all. It doesn't emit light, doesn't absorb it, doesn't reflect it. Photons pass through dark matter as if it weren't there. To light dark matter is a ghost. Yet, its gravity is real powerful, shaping the cosmos on the largest scales. Think of it this way. If you could remove all the normal matter from the universe, every star, planet, gas cloud, every atom we're made of, the structure would remain. Dark matter forms a cosmic scaffolding, a web threading through space, and galaxies form along its strands like dew on a spider's web. We're not the main event. We're decorations on a framework we cannot perceive. So, what is it? Decades of research have proposed candidates. WIMPs, weakly interacting, massive particles are a popular guess. Theoretical particles that have mass and gravity but barely interact with ordinary matter. Physicists have built detectors deep underground, shielded from cosmic rays, waiting for a WIMP to collide with an atomic nucleus. Just one collision would be enough. One tiny spark of confirmation in tanks filled with liquid xenon, cooled to unimaginable cold, monitored by sensors so sensitive they can detect a single photon. The LUX experiment in South Dakota, the Xenon 1T detector in Italy, the Panda X experiment in China, all waiting in silence and darkness for a whisper of interaction. Months pass, years. The detectors see nothing. Or rather, they see cosmic rays' radioactive decay from trace elements in the surrounding rock, the occasional neutron sneaking through shielding, but nothing that looks like dark matter. Each null result tightens the constraints, narrows the possibilities. If WIMPs exist, they're more elusive than anyone hoped. Other candidates exist. Axion's hypothetical particles, a billion times lighter than electrons swarming through space in numbers too vast to count. MACHOs, massive astrophysical compact. Halo objects, failed stars, black holes, dense objects that emit little light but carry mass. Primordial black holes formed in the first moments after the Big Bang, small enough to drift through galaxies without detection. Each possibility solves some problems, creates others. Have you ever felt certain something was there, even though you couldn't see it? That's the position astrophysics finds itself in. Every observation points to dark matter's existence, yet it refuses direct detection. It's like knowing someone is in the room because you hear breathing, but when you turn on the light, no one's there. Gravitational lensing gives us one of the clearest glimpses. When light from a distant galaxy passes near a massive object, gravity bends its path, warping the image. Einstein predicted this, and observations confirmed it. Now, we use lensing as a map. By studying how light bends, we can trace where mass concentrates, even mass we can't see. And the maps reveal dark matter halos surrounding galaxies vast and diffuse, extending far beyond the visible edges. The Bullet Cluster offers particularly striking evidence. Two galaxy clusters collided, and when astronomers studied the aftermath, they found something remarkable. The visible matter, hot gas glowing in X-rays, had slowed down during the collision, interacting and creating drag. but the dark matter passed through itself unimpeded, like two swarms of ghosts interpenetrating without resistance. Gravitational lensing showed where the mass actually was, and it didn't match the visible gas. Dark matter and normal matter had separated cleanly, proving they behave differently. It's some of the most compelling evidence that dark matter isn't just a mathematical trick. It's real physical out there. Yet, for all we know, we're still groping in conceptual darkness. Modified Newtonian dynamics. Mond proposes that maybe gravity itself behaves differently at galactic scales. Perhaps the inverse square law breaks down over vast distances, and what we're calling dark matter is just gravity doing something unexpected. Mond works well for some galaxies, less well for others. Most physicists favor dark matter, but Mond reminds us that confidence isn't certainty. There's something humbling about this. Humans have walked on the moon. We've split atoms, sequenced genomes, photographed black holes. We've built particle accelerators that smash protons together at near light speed to glimpse the fundamental forces of nature. And yet, we don't know what most of the universe is made of. 85% invisible, 85% mystery. Children often ask why scientists don't just look harder, build better microscopes, point bigger telescopes at the problem. But dark matter doesn't hide behind distance or smallness. It hides behind a more fundamental invisibility. It's like asking someone who's colorblind to see red by trying harder. The tools we have, telescopes, detectors, photon-based instruments, all rely on light. And dark matter doesn't speak that language. So we search indirectly. The European Space Agency's Euclid telescope launched in 2023 maps the distribution of dark matter across billions of light years by observing how it lenses background galaxies. NASA's Nancy Grace Roman Space Telescope will continue this work, refining our maps, testing whether dark matter's properties remain constant across cosmic time. Each mission adds pixels to a picture. We're assembling one inference at a time. Some researchers suggest dark matter might interact with itself in ways we haven't detected. Dark photons, dark forces, an entire dark sector of physics running parallel to the one we know. If true, there could be dark stars, dark planets, entire structures composed of particles invisible to us, existing alongside our universe in a kind of shadow reality. We'd never see them, never touch them, but their gravity would anchor ours. It's worth remembering how often science has revealed layers beneath what seemed fundamental. Atoms were once considered indivisible. Then we found electrons, protons, neutrons, then quarks and gluons inside protons, then hints of something deeper still. Each layer peeled back exposes new complexity. Maybe dark matter is another layer. Maybe it's simpler than we think or stranger. Maybe it's not one thing, but several a category we've invented to hold mysteries we haven't differentiated yet. Vera Rubin never won the Nobel Prize for her discovery, though many believe she deserved it. She spent decades fighting for recognition in a field that didn't always welcome women. When she applied to graduate school at Princeton, she was rejected not for lack of qualifications, but because Princeton didn't accept female astronomy students until 1975. She persisted, observed, calculated, let the data speak. And the data told a story so strange, it took the world decades to listen. She once said, "In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade." If Rubin's right, we're children staring at a universe where most of the pieces are invisible. We're learning to navigate by feeling edges, by watching how visible things move in response to invisible pulls. And maybe that's okay. Maybe knowing we don't know is a kind of wisdom. The universe doesn't owe us transparency. It doesn't owe us answers written in light and equations. What we have, this growing map of gravitational influence, this evidence of structure beyond sight, might be as close as we get. And within that limitation lies a strange beauty. We're creatures of light, carbon, and oxygen bound by chemistry that depends on photons. Yet, we've learned to perceive beyond our senses to detect presence through absence, to map the invisible by watching how it shapes the visible. Dark matter holds galaxies together, holds clusters together, holds the large-scale structure of the universe in a web we're only beginning to trace. Without it, galaxies would never have formed. Stars wouldn't ignite, planets wouldn't coalesce, we wouldn't exist. This invisible scaffolding isn't just background, it's foundation, the skeleton beneath everything we see. So, while we wait for detectors to click, for theories to sharpen, for some brilliant mind to solve what has eluded thousands, we can rest in the knowledge that mystery doesn't diminish reality. It enriches it. The universe is larger, stranger, more layered than appearances suggest. And we, made of stardust and shaped by forces we're only beginning to name, are part of that strangeness. The invisible holds us together, and somewhere in the dark, answers wait patient and silent as gravity itself. But the cosmos doesn't only hide in invisibility. Sometimes it announces itself suddenly, brilliantly, with bursts of energy that cross unimaginable distances just to catch our attention for a fraction of a second. Somewhere in the depths of space, something screams, just once. A burst of radio energy so intense it releases more power in a millisecond than the sun produces in 3 days. Then silence, as if the universe blinked and in that blink shouted. These are fast radio bursts, and we have no idea what makes them. The first one appeared in 2007, though it had actually occurred 6 years earlier. Australian astronomer Duncan Lorimer was sifting through archived data from the Parkes radio telescope, looking at old pulsar observations, when he found something that shouldn't exist. A spike in the radio signal, incredibly brief, incredibly bright, coming from a direction in space billions of light years away. The energy required to produce such a flash was staggering. Whatever created it had unleashed in less time than a heartbeat energy equivalent to what our entire civilization has produced throughout human history. Lorimer checked for errors, equipment malfunction, interference from Earth-based sources, cell phones, microwaves, passing aircraft. Radio telescopes are sensitive instruments, and false signals are common, but the burst was real. It had the signature of something cosmological, distant, powerful, fleeting. It became known as the Lorimer Burst, and for years it stood alone. A single mystery, an anomaly you could almost dismiss. Then we found more, and more. Fast radio bursts, FRBS, started appearing in telescope data with unsettling regularity. Some came from random directions. Others seemed clustered. Most lasted just a few milliseconds. Blink and you'd miss them. Except, telescopes don't blink and the data doesn't lie. By 2024, astronomers had cataloged hundreds of these bursts, each one a pulse of energy crossing the cosmos to tap us on the shoulder and vanish before we could ask questions. Here's what makes them strange. The bursts are dispersed. As radio waves travel through space, they interact with free electrons in the interstellar medium, and different frequencies arrive at slightly different times. Scientists can measure this dispersion and calculate how far the signal traveled. The numbers are staggering. Billions of light years. These aren't local events, they're cosmological. Something out in the deep universe is generating radio flashes bright enough to be detected across distances so vast that light from those regions left long before Earth even formed. At first, scientists suggested they might be pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. But pulsars repeat. They're periodic, predictable. Most FRBS don't repeat. They fire once and go silent. One flash, one riddle, then nothing. Except for FRB 121102. Discovered in 2012, this burst did something unprecedented. It repeated. Not regularly, not predictably, but it flashed again. And again. Over the years, telescopes caught dozens of bursts from the same location in space. This changed everything. A repeating source could be studied, tracked, analyzed. Astronomers pinpointed its origin to a dwarf galaxy 3 billion light-years away. Whatever was producing these bursts, it wasn't a one-time cataclysm. It was ongoing. The leading candidate for FRB origins is magnetar's neutron stars, with magnetic fields so powerful they warp the vacuum of space itself. A magnetar's magnetic field is trillions of times stronger than Earth's, strong enough to pull the iron from your blood if you got too close. These objects are the universe's most extreme magnets, and when their crusts crack or their magnetic fields suddenly realign, they can release tremendous energy in a brief, violent flash. In April 2020, astronomers detected an FRB coming from within our own galaxy. For the first time, a fast radio burst originated close enough that we could investigate its source. It came from a known magnetar, SGR 1935 plus 2154, located about 30,000 light-years away, practically next door in cosmic terms. Observations confirmed the magnetar had released a burst of X-rays and gamma rays at the same moment as the radio pulse. Finally, a connection, evidence that at least some FRBs come from magnetars. But not all mysteries dissolved. Some FRBs are far brighter than what that magnetar produced. Some repeat in patterns that don't match magnetar behavior. FRB 180916 repeats on a 16-day cycle, active for 4 days, silent for 12 like clockwork. Why, no one knows. Magnetars don't operate on schedules. Some researchers suggest the periodicity might come from the magnetar orbiting another object, with the burst emissions beamed in a specific direction that sweep past Earth only during certain phases of the orbit. Possible, but unconfirmed. Then there's FRB 201905220B, discovered in 2019. Unlike most FRBs, which appear to originate from relatively empty regions of space, this one sits in an extremely dense environment, surrounded by gas and plasma. The radio waves get scattered and delayed as they pass through, creating a messy signal. It's like trying to hear someone shouting from inside a cloud. The environment itself becomes part of the puzzle. What kind of event produces FRBs in such chaotic neighborhoods? Some scientists speculate about more exotic sources: colliding neutron stars, black holes devouring matter in sudden gulps, cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe snapping under tension. Even more speculative ideas involve primordial black holes or strange quark matter. Each hypothesis explains some observations, fails to explain others. And then there are the outliers. FRB 202000120. E, detected in 2020, comes from a globular cluster in the nearby galaxy M81, only 12 million light-years away. Globular clusters are ancient, densely packed groups of old stars. They shouldn't host magnetars, which are young, formed from massive stars that live fast and died violently. Yet, here was an FRB repeating, coming from a place where the source shouldn't exist. The universe, it seems, refuses to follow the rules we try to impose. Have you ever received a message you couldn't read? Not because the language was foreign, but because you didn't know it was a message at all. That's the position we're in with FRBs. We detect the signal, we measure its properties, but we don't know if it means anything. Are these bursts purely natural byproducts of violent astrophysical processes, or could some, however unlikely, be artificial? The idea isn't as far-fetched as it sounds. In 2017, physicists Manasvi Lingam and Abraham Loeb published a paper exploring whether advanced civilizations might use powerful radio beams to propel spacecraft. If you focus enough energy into a beam and bounce it off a light sail, you could accelerate a ship to relativistic speeds. From Earth, such a beam would look exactly like a fast radio burst, brief, intense, directional. If we happened to be in the path of the beam, we'd see a flash and then nothing as the beam swept past. Most scientists consider this unlikely. The energy requirements would be enormous, and the beams would need to be aimed with extraordinary precision across interstellar distances. It's far more probable that FRBs are natural phenomena we simply don't yet understand. But the possibility lingers. Every time a new FRB appears, there's a moment brief as the burst itself where we wonder. Detection is getting better. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, began operations in 2018 and revolutionized FRB astronomy. Unlike traditional telescopes that point at specific targets, CHIME watches a huge swath of sky, simultaneously detecting dozens of FRBs per month. The flood of data has allowed researchers to categorize bursts, identify patterns, rule out hypotheses. We're moving from anecdotes to statistics, from mystery to science. Yet each answer breeds new questions. Why do some FRBs repeat while others don't? Why do the repeating ones show such different behaviors? What determines the burst duration, brightness, frequency? Some last a millisecond, others stretch to a few seconds. Some emit across a narrow range of frequencies, others span the spectrum. The diversity suggests multiple mechanisms, or perhaps a single mechanism with wildly different conditions. There's something almost poetic about FRBs. They travel for billions of years, crossing a universe that's expanding, passing through clouds of gas around galaxies threading the cosmic web. The signal weakens, disperses, but persists. And then by chance, by the alignment of instruments and timing, the burst reaches Earth. A radio telescope happens to be listening. The data gets recorded. And humans, creatures who've only been looking at the radio sky for a few decades, catch a whisper from the deep. Most FRBs come from distances so great that when the burst was emitted, Earth was a different planet. Dinosaurs might have still walked, or perhaps life was just beginning to crawl from the oceans. The light we see from distant galaxies shows us the past. FRBs do the same, but louder, stranger, carrying energy across epochs. Some researchers compare studying FRBs to forensic science. You arrive at a crime scene long after the event. No witnesses, just evidence, a scattering of data points. You measure, analyze, reconstruct. You build models of what might have happened, test them against observations, refine, or discard. Progress comes slowly, inference by inference. The challenge is humbling. With pulsars, we can observe them continuously, watch them spin, measure their slowdown, build detailed models. With FRBs, we get a snapshot, a single moment of violence frozen in data. It's like trying to understand a thunderstorm by catching one raindrop. And yet, persistence pays. The more FRBs we detect, the clearer patterns emerge. Distance distributions, energy profiles, host galaxy types, repetition rates. Each new burst adds a pixel to a picture we're assembling, without knowing what it depicts. Maybe in a decade, FRBs will be understood, cataloged, explained. Or maybe they'll remain on the edge of comprehension, just strange enough to keep us guessing. What's certain is the universe is more active than we realized. It's not a static backdrop of stars and silence. It pulses, flashes, shouts and frequencies we're only beginning to monitor. And every shout is a reminder that out there in the cold and dark processes unfold that dwarf anything we've created. Magnetars cracking, stars colliding. Exotic matter behaving in ways our physics struggles to predict. Fast radio bursts are cosmic telegrams without return addresses. They arrive, deliver their burst of energy, and leave us wondering who sent them, why, and whether they'll speak again. It's the kind of mystery that keeps astronomers awake, not with worry, but with excitement. Because every mystery is an invitation, a chance to learn something fundamental about how the universe works. So we keep listening. Telescopes scan the sky, recording every flicker, every pulse. Algorithms sift through noise, flagging anomalies. Researchers gather, debate, hypothesize. And somewhere out there in a galaxy, we may never visit, another burst is forming, building energy, preparing to shout across billions of years of cosmic history. When it reaches us, we'll be ready, or at least we'll be listening. Sometimes, though, the universe doesn't just send signals. Sometimes it sends objects, strange travelers passing through our solar system, moving too fast to stay too odd to ignore. Imagine waiting by a phone for 50 years, hoping for a call that never comes. Then one night, it rings. You answer. Static. A voice, maybe. And before you can say hello, the line goes dead. You'll spend the rest of your life wondering who called and why they hung up. That's what happened on August 15th, 1977. Except the phone was a radio telescope, and the caller might have been 3 billion light years away. On that warm summer night, the Big Ear radio telescope in Ohio was doing what it always did, scanning the sky, listening for signals that didn't belong. Most of what it heard was noise, cosmic static, interference from Earth, the hum of a universe filled with natural radio sources, but devoid of voices. Then at 11:16 p.m. something changed. For 72 seconds, the telescope detected a signal so strong, so strange, so perfectly structured that it seemed to defy natural explanation. The signal peaked at 1,420 megahertz, the frequency at which hydrogen, the most abundant element in the universe, naturally emits radio waves. Scientists had long theorized that any civilization trying to communicate across space might choose this frequency precisely because it's universal, a cosmic calling card. The signal was narrow-band focused, unlike the broad-spectrum noise that stars and galaxies produce. It rose in intensity, peaked, then faded as the telescope's field of view swept past the source, exactly as you'd expect from a stationary point in space. Jerry Amon, a volunteer astronomer reviewing the data printout days later, saw the sequence 6EQUJ5. These alphanumeric characters represented signal strength over time, climbing from background noise to a peak 30 times stronger than anything around it. Amon grabbed a red pen and circled the sequence, scribbling in the margin a single word: wow. That word became its name. The WOW signal. And for over 45 years, it has remained one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Here's what we know. The signal came from the direction of the constellation Sagittarius near the Chi-Sagittarii star group. It bore none of the hallmarks of interference. No satellites passed overhead at that moment. No aircraft. No terrestrial broadcasts on that frequency. The Big Ear telescope had 2 feed horns that scanned the sky in parallel, separated by a few minutes of observation time. The signal appeared in one feed horn, but not the other, suggesting it was extremely brief or precisely timed. Either it lasted only as long as the telescope could see it, or it started and stopped within that narrow window. Astronomers have returned to that patch of sky hundreds of times since 1977, using more sensitive instruments, wider frequency ranges, longer observation periods. They've found nothing, no repeat transmission, no follow-up. Just silence as deep and complete as the silence before. It's as if someone knocked on the door once, and when we opened it, no one was there. The explanations fall into 2 camps, natural and artificial. Natural sources include comets releasing clouds of hydrogen as they heat up near the sun, creating brief, bright radio emissions. In 2017, astronomer Antonio Paris proposed that 2 comets, 266P/Christensen and 335P/Gibbs, were in the region of sky where the WOW signal originated. Comets weren't cataloged there in 1977 because they hadn't been discovered yet. When Paris tested this hypothesis by observing the comets at the same frequency, they did emit radio signals. Case closed, not quite. Other researchers pointed out that the WOW signal's characteristics didn't perfectly match cometary emissions, and the hypothesis remains debated. Then there's the possibility no one wants to say too loudly, but everyone thinks about. What if it was artificial? What if for 72 seconds, a distant civilization pointed a transmitter at Earth, sent a pulse, and moved on? Not a message, there was no information encoded, no pattern beyond the signal's existence, but a beacon, a lighthouse flash. Hello, we're here. Are you? If so, why only once? Maybe they're broadcasting in all directions, sweeping the galaxy, and Earth just happened to be in the beam for a moment. Maybe they only transmit sporadically, conserving energy, and we've been listening during the silences. Or maybe the signal wasn't meant for us at all. Imagine overhearing a conversation in a crowded room, just one sentence stripped of context, and then the speakers move away. You'd never know what they were discussing, only that they spoke. The frustration of the WOW signal is its incompleteness, its evidence without conclusion, a riddle presented once and never repeated. And that single occurrence makes it scientifically slippery. Science thrives on repeatability. One anomaly can be dismissed as error, glitch, coincidence, but the data seems clean. The telescope functioned properly. The signal's characteristics align with what SETI researchers have long predicted an artificial transmission might look like. Yet without confirmation, without a second occurrence, it remains suspended between mystery and mistake. Fast forward 40 years. October 19th, 2017. Astronomers at the Pan-STARRS telescope in Hawaii noticed something odd in their data. An object moving through the inner solar system, but not on an orbit that belonged. Most objects near the Sun, asteroids, comets follow elliptical paths bound by gravity, returning periodically. This object was moving too fast. Its trajectory was hyperbolic, meaning it came from outside the solar system and would leave again, never to return. It was humanity's first confirmed detection of an interstellar visitor. They named it Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. And from the moment astronomers started studying it, nothing made sense. First, the shape. Most asteroids are roughly spherical or lumpy, shaped by gravity and collisions. Oumuamua was elongated cigar-shaped, or perhaps pancake flat, depending on interpretation. Initial estimates suggested it was about 10 times longer than it was wide, tumbling end over end as it traveled. No natural object we'd ever seen had proportions like that. It looked more like something designed than something formed by cosmic chance. Then, the brightness. As Oumuamua tumbled, its reflected light varied dramatically, suggesting a surface that was either highly reflective or unusually shaped. Some researchers proposed it might be metallic, others suggested ice. Still others wondered if it was a fragment of a larger object sheared off by some cataclysm billions of years ago and sent drifting through interstellar space. But the strangest detail came when scientists analyzed its trajectory. As Oumuamua swung around the sun and headed back out into the darkness, it accelerated. Not much, just a tiny push, barely detectable, but it was there. Comets do this when sunlight heats their ice, causing jets of gas to erupt and create thrust. But Oumuamua showed no signs of outgassing, no tail, no coma, no detectable emissions. Yet something was pushing it. Harvard astronomer Avi Loeb proposed an explanation that ignited controversy. What if Oumuamua wasn't a comet or asteroid at all, but a light sail, a thin sheet of material pushed by radiation pressure from starlight? Such sails have been proposed as a way to travel between stars without fuel. If Oumuamua was artificial, its odd-shaped reflectivity and non-gravitational acceleration would make sense. It would be a piece of technology, either functional or derelict, drifting through space long after its creators vanished. Most astronomers disagreed. They argued that natural explanations, however strange, remained more plausible than invoking alien engineering. Perhaps Oumuamua was made of hydrogen ice, a material that would sublimate without producing a visible tail. Perhaps it was a cosmic dust bunny, held together by forces we don't fully understand. Perhaps our observations were incomplete and a simpler explanation lurked in the data we didn't collect. Because here's the problem. Oumuamua came and went too quickly. By the time astronomers realized what they were looking at, it was already leaving. Telescopes scrambled to gather data, but the object was small, distant, and moving fast. Within weeks, it was too faint to observe. We got a glimpse, a tantalizingly brief look, and then it was gone, receding into the blackness between stars. Do you ever wonder what we missed? If we'd had more time, better instruments advance. Warning, what might we have learned? Spectroscopy could have revealed its composition in detail. Radar might have mapped its surface. Close-up imaging could have settled questions about shape and structure. But we didn't get that chance. Oumuamua slipped through our solar system like a stranger passing through a room, and we barely had time to notice before the door closed. The debate over its nature continues. In 2019, astronomers proposed that Oumuamua might be a fragment of a planet torn apart by tidal forces as it passed too close to a star. The fragment stretched and flattened, could have the elongated shape observed. In 2021, researchers suggested it might be a nitrogen iceberg, similar to the surface of Pluto, explaining both the reflectivity and the lack of visible outgassing. Each hypothesis fits, some data contradicts others. Loeb's light sail idea remains the most controversial, not because it's impossible, but because it invokes the extraordinary. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." And we don't have that evidence. What we have is an object that behaved oddly, defied easy categorization, and left before we could investigate properly. That's not proof of alien technology. It's proof of our limitations. Yet, the possibility lingers. Because if Oumuamua was artificial, it wouldn't be a recent launch. It had been traveling through interstellar space for millions, perhaps hundreds of millions of years. Whatever civilization might have built it could be long gone. We might be finding their debris the remnants of a species that reached for the stars and then faded into silence. Or perhaps it's still operational, a probe designed to last eons, observing recording, transmitting data back to a home that no longer listens. The odds of detecting an interstellar object are slim, space is vast, and objects are small. That we spotted Oumuamua at all was luck. It passed close enough to the sun to be bright enough to detect. How many others have slipped through unseen? How many pass through the outer solar system, too faint, too distant for our telescopes to notice? Since Oumuamua, we found one more, two. I/Borisov, an interstellar comet discovered in 2019. Borisov behaved like a comet, outgassing, tailed, unremarkable, except for its origin. It followed the script we expected. Oumuamua did not, and that's what keeps it in conversation. It's the outlier, the anomaly, the visitor that didn't fit the pattern. Scientists suggest that as telescope technology improves, we'll detect more interstellar objects, perhaps dozens per year, perhaps hundreds. And with each one, we'll learn whether Oumuamua was an oddity or the first glimpse of something common we've simply never noticed before. Maybe interstellar space is full of debris fragments, ice rock remnants of planetary systems torn apart by stellar violence. Maybe some of it is stranger still. The WOW signal and Oumuamua share something fundamental: their encounters without closure. A signal heard once, an object seen briefly, both tantalizing, both incomplete, both leaving us with more questions than answers. And maybe that's fitting. The universe doesn't owe us explanations. It doesn't arrange itself for our convenience. What we have are moments, a 72-second transmission, a few weeks of observation, brief intersections between human curiosity and cosmic phenomena. And in those moments, we glimpse something larger, a universe not empty, not silent, but full of motion and mystery. Whether the sources are natural or artificial almost doesn't matter. What matters is the reminder that we're watching a story unfold in real time, and we've only seen the opening pages. So we keep listening, keep watching. The next interstellar visitor could arrive any year now, and this time we'll be ready. Better telescopes, faster response. Maybe we'll get the answers Oumuamua denied us. Or maybe we'll find new mysteries deeper and stranger still. Either way, the night sky holds more than stars. It holds visitors' signals, whispers from the deep. And somewhere out there, perhaps, something is listening too. But if the cosmos sends puzzles and bursts and visitors, it also leaves clues in its oldest light echoes from the very beginning, carrying secrets we're only starting to decode. If you could take a photograph of the universe when it was just a baby, 380,000 years old, what would you see? Not stars, not galaxies, just light. A faint glow cooling from white-hot to red, spreading evenly in all directions. That photograph exists. We call it the cosmic microwave background. And hidden in its details are imperfections that shouldn't be there, flaws in the universe's baby picture, cracks in the echo of creation itself. In 1964, two engineers named Arno Penzias and Robert Wilson were testing a radio antenna at Bell Labs in New Jersey. They kept picking up noise, a persistent hiss that wouldn't go away no matter where they pointed the antenna. They checked for interference, cleaned out pigeons nesting in the equipment. The noise remained, uniform, unchanging, coming from everywhere at once. What they'd stumbled upon was the afterglow of the Big Bang, light that had been traveling through space for nearly 14 billion years, stretched by the universe's expansion from visible wavelengths into microwaves. It's the oldest light we can see, a snapshot of the cosmos, when it first became transparent when electrons and protons combined into neutral hydrogen and photons could finally travel freely. Before this moment, the universe was opaque, a fog of charged particles scattering light in all directions. After it cleared and light began its long journey to us, Penzias and Wilson won the Nobel Prize for their discovery, though they had been looking for something entirely different. Sometimes the universe hands you answers before you know what questions to ask. The cosmic microwave background. The CMB is remarkably uniform. Its temperature is 2.725 Kelvin, just a few degrees above absolute zero, and it varies by only tiny fractions across the sky. These variations, called anisotropies, represent the seeds of structure in the early universe. Regions slightly denser than average would eventually collapse under gravity to form galaxies. Regions slightly less dense would become the voids between them. The CMB maps the blueprint of everything that followed. In the 1990s, NASA launched the Cosmic Background Explorer, COBE, to measure the CMB with unprecedented precision. The results were stunning. The temperature fluctuations matched predictions from Big Bang theory almost perfectly. But when scientists looked closer, they found something strange. A region of sky about 5 degrees across in the constellation Eridanus was colder than it should be, significantly colder. They called it the cold spot. At first, researchers assumed it was a statistical fluke. When you analyze enough data, random patterns emerge. But as better measurements came in from the Wilkinson Microwave Anisotropy Probe, then the Planck satellite, the cold spot, persisted. It was real. A patch of the early universe that was inexplicably colder than its surroundings, with no clear explanation from standard cosmology. One hypothesis suggests the cold spot might be caused by a supervoid, a vast region of space with fewer galaxies than average. As CMB photons pass through such a void, they lose energy through a process called the integrated Sachs-Wolf effect. But surveys of that region of sky haven't found a void large enough to explain the temperature deficit. The structures we observe don't match the anomaly we detect. Another idea, more speculative, proposes that the cold spot could be a bruise, a place where our universe bumped into another universe. In multiverse theories, countless universes exist, separated by dimensions we can't perceive. If two universes collided in the distant past, the collision might leave an imprint on the CMB, a scar from an encounter we'll never witness directly. It sounds like science fiction, but some physicists take it seriously enough to develop testable predictions. So far, the data doesn't confirm or rule out the hypothesis. The cold spot remains an open question. Then there's the axis of evil, not a political reference, but a nickname given to another CMB anomaly. When scientists analyze the temperature fluctuations in the CMB, they break them down into different scales: large patterns, medium patterns, small patterns. These patterns should be randomly oriented, scattered across the sky, with no preferred direction. The universe, we assume, has no special axis, no cosmic up or down, no center. But the largest fluctuations in the CMB don't appear random, they align. Researchers found that certain temperature patterns are oriented along a particular axis, as if the early universe had a direction, a preference, something that picked out one axis over others. It's subtle, it shouldn't exist, and yet multiple independent analyses confirm it. The alignment is real. The nickname Axis of Evil came from a frustrated cosmologist who joked that the anomaly was so problematic it deserved an ominous name. The name stuck, because if the axis is real, if it's not a measurement error or a coincidence, it challenges fundamental assumptions about cosmology. It suggests the universe might not be isotropic, not the same in all directions. And if the universe has a preferred direction, our models need revision. Some scientists argue the axis is an artifact of how we observe the CMB from our particular location in space. The Milky Way sits in a specific spot, moving in a specific direction, and local structures could create apparent alignments. But researchers have tried to filter out these effects, and the axis persists. Others suggest it might be a sign of new physics, something happening in the very early universe before inflation that left an imprint we're only now detecting. Have you ever looked at something familiar and noticed a detail that didn't belong? A crack in a wall you'd walked past 1,000 times? That's what these anomalies feel like to cosmologists. The CMB has been studied for decades. It's one of the most precisely measured phenomena in all of science, and yet, hidden in its uniformity are features that resist explanation. The CMB is also a test of the Big Bang theory itself. If the universe began in a hot, dense state and expanded, cooling as it grew, then the CMB should exist exactly as we observe it. And largely it does. The temperature, the spectrum, the distribution of fluctuations all match predictions. But science is built on exceptions. It's the anomalies, the data points that don't fit that drive discovery. Newton's laws worked perfectly until Mercury's orbit didn't quite match predictions, and that discrepancy helped lead to Einstein's theory of relativity. So, when we find a cold spot or an axis of evil, we don't dismiss them. We investigate, we check instruments, we gather more data, we propose explanations, test them, refine, or discard. Because either these anomalies will resolve into mundane causes, measurement errors, local contamination, statistical quirks, or they'll point towards something profound. New physics, new cosmology, new understanding of how the universe began. The Planck satellite launched by the European Space Agency in 2009 provided the most detailed map of the CMB to date. Its measurements are so precise that scientists can test cosmological models with astonishing accuracy. The standard model of cosmology, lambda CDM, which includes dark matter and dark energy, fits the Planck data almost perfectly. Almost. Small tensions remain. Parameters measured one way give slightly different values than parameters measured another way. The differences are small, but they're there, and they refuse to disappear even as measurements improve. One tension involves the Hubble constant, the rate at which the universe is expanding. Measurements of the CMB suggest one value. Measurements of distant supernovae suggest another. The difference is only a few percent, but it's persistent and statistically significant. Either one set of measurements is wrong, or our model of the universe is incomplete. Something is missing, and we don't know what. Another puzzle involves the CMB's quadrupole and octupole moments large-scale temperature patterns. These should have certain amplitudes based on standard cosmology, but the observed values are lower than expected. It's not a huge discrepancy, but it's noticeable. Some researchers call it the low L anomaly, referring to the low multipole moments in the CMB's power spectrum. It could be a statistical fluke, or it could be telling us something about the universe's geometry, its topology, the way space itself is shaped. Topology sounds abstract, but it has real implications. Imagine the universe isn't infinite, but finite and curved in on itself, like the surface of a sphere or a donut. In such a universe, light could travel around the whole cosmos and return to its starting point. The CMB would reflect this, showing patterns that repeat or correlate in specific ways. Some models of finite universes predict exactly the kinds of anomalies we see: suppressed large-scale fluctuations, preferred axes cold spots. But proving this requires evidence beyond the CMB, and so far we don't have it. There's also the question of what came before the CMB. Before the universe became transparent, it was opaque, a hot plasma where photons scattered constantly. We can't see through that fog directly, but we can infer what happened earlier by studying the patterns imprinted on the CMB. Inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, is thought to have smoothed the universe, explaining why the CMB is so uniform. Tiny quantum fluctuations during inflation got stretched to cosmic scales, seeding the structure we see today. But inflation itself raises questions. What caused it? What ended it? Different models of inflation make slightly different predictions, and some match the data better than others. The CMB provides a testing ground, but the signals are subtle. Small differences in temperature fluctuations, polarization patterns, statistical correlations, these are the clues. And hidden among them might be evidence of what triggered the universe's birth. Some physicists propose that the Big Bang wasn't the beginning, but a transition. A universe before ours collapsed, rebounded, and became the universe we inhabit. This cyclic model predicts different CMB anomalies than standard inflation. So far, the data leans toward inflation, but the cyclic model hasn't been ruled out. The anomalies we observe could be signatures of a previous universe, echoes of a cosmos that existed before time as we know it began. It's humbling to realize how much we infer from so little. The CMB is just light photons that have been traveling for eons, carrying information encoded in their temperature and polarization. We can't touch it, can't sample it, can't run experiments on it. We can only observe and interpret. And interpretation requires assumptions. We assume the laws of physics were the same in the early universe as they are now. We assume our instruments measure accurately. We assume our mathematical models capture reality. Any of these assumptions could be slightly wrong, and the anomalies we see might be telling us where. Researchers compare the CMB to archaeology. You dig up fragments, piece them together, build a picture of the past. But the picture is incomplete. Some pieces are missing. Others are worn, ambiguous. You make educated guesses, revise as new evidence emerges. The CMB gives us fragments from the universe's infancy, and we're still learning how to read them. Meanwhile, the anomalies persist. The cold spot hasn't warmed. The axis of evil hasn't randomized. The low L problem hasn't resolved. Each new telescope, each refined analysis confirms their presence. They're not going away, which means we need better theories, better models, better understanding of what the early universe was doing and why it left these particular marks. Some scientists find the anomalies exciting. They're hints that our story of the cosmos isn't complete. Others find them frustrating. Cosmology was converging on a coherent picture, and these details refuse to fit neatly. But that's how science works: messy, iterative, full of puzzles that don't yield easily. The CMB also reminds us of scale. We're looking at light from when the universe was a fraction of its current age. The structures we see imprinted on it, density fluctuations, temperature variations, were tiny then. But they grew into galaxies, clusters, the cosmic web. Everything around us traces back to those early patterns. We are in a literal sense descendants of CMB fluctuations. The atoms in our bodies were forged in stars that formed along the scaffolding laid down in the first moments after the Big Bang. And if there are cracks in that scaffolding, imperfections in the blueprint, they matter because they shaped everything. A slightly colder region might have delayed galaxy formation nearby. A preferred axis might have influenced how matter clustered. The universe we inhabit is the product of every tiny variation in the CMB, amplified over billions of years. So we keep mapping, keep measuring. Future missions will study the CMB's polarization with even greater precision, searching for signatures of gravitational waves from inflation testing, whether the anomalies hold clues to physics beyond the standard model. Maybe we'll find that the cold spot and axis of evil are just quirks, rare but natural fluctuations in an otherwise uniform cosmos. Or maybe they'll open doors to new realms of understanding. Either way, the universe's baby picture isn't perfect, and that imperfection is beautiful. It's a reminder that even the most fundamental structures carry mysteries, that the cosmos, for all its elegance, refuses to be entirely predictable. From the faint glow of ancient light, we've learned the universe's age composition history. We've confirmed theories, ruled out alternatives, refined our models. And still, the CMB whispers secrets we haven't fully decoded. Cracks in the echo, flaws in the foundation, invitations to look deeper, question harder. Imagine possibilities we haven't yet conceived. Yet the strangeness doesn't stop at light and structure. Even the connections between things, bonds we assume are bound by distance, turn out to be far more mysterious than they should be. Imagine holding two coins. You flip one in New York, and instantly faster than light could travel between them, the other coin in Tokyo lands on the opposite side. Not because they're connected by signals or hidden wires, but because somehow, impossibly, they remember each other. This isn't magic, it's quantum mechanics. And Einstein hated it. In 1935, Albert Einstein co-authored a paper with physicists Boris Podolsky and Nathan Rosen. They weren't celebrating a discovery, they were launching an attack. The target was quantum mechanics, specifically a prediction so strange that Einstein believed it exposed a fatal flaw in the theory. The paper became known as the EPR paradox, and at its heart was a phenomenon that would later be called quantum entanglement. Here's what bothered Einstein. Quantum mechanics suggested that two particles could become correlated in such a way that measuring one instantly affected the other, no matter how far apart they were. If you measured the spin of one electron and found it pointing up, its entangled partner would instantly be found pointing down, even if it was on the other side of the galaxy. The correlation wasn't just statistical, it was absolute, immediate, as if distance meant nothing. Einstein called this spookhafte Fernwirkung, spooky action at a distance. He didn't believe it. To him, it violated a fundamental principle: nothing can travel faster than light, including information. If measuring one particle affected another instantaneously, it seemed to imply faster than light communication, which relativity forbids. Einstein concluded that quantum mechanics must be incomplete. There had to be hidden variables, information the particles carried with them, that determined outcomes in advance. The particles weren't communicating. They were just following instructions written into their fabric from the start. For decades, the debate remained philosophical. Quantum mechanics worked beautifully for predictions, but the question of what it meant, whether particles truly influenced each other across space or simply appeared to, was unsettled. Then in 1964, physicist John Bell changed everything. Bell derived an inequality, a mathematical test that could distinguish between Einstein's hidden variable theories and genuine quantum entanglement. If hidden variables existed, experiments would show correlations up to a certain limit. If entanglement was real, the correlations would exceed that limit. It was elegant, testable, and it turned a philosophical argument into an experimental question. The first tests came in the 1970s and 1980s, conducted by physicists like John Clauser and Alain Aspect. They created pairs of entangled photons, separated them, and measured their polarizations. The results violated Bell's inequality. The correlations were stronger than any hidden variable theory could explain. Quantum entanglement wasn't just real, it was exactly as strange as quantum mechanics predicted. Einstein, who had died in 1955, never saw these results. But his intuition was wrong. The universe, it turns out, allows for connections that transcend distance in ways relativity doesn't forbid. Because here's the trick, entanglement doesn't transmit information. You can't use it to send messages faster than light. When you measure one particle, you instantly know something about its partner, but you can't control what you measure. The outcomes are random, correlated, but random. So, while the connection is instantaneous, it's also useless for communication. Think of it this way. Two people each hold a sealed envelope. When one opens theirs and finds a red card, they instantly know the other envelope contains a blue card. The knowledge is instantaneous, but no information traveled. The correlation was established when the envelopes were prepared, even though quantum mechanics tells us the color wasn't determined until the moment of measurement. It's this wasn't determined part that makes entanglement so profoundly strange. In classical physics, things have definite properties whether we measure them or not. A ball is either red or blue, whether you look at it or not. But in quantum mechanics, particles exist in superposition simultaneously in multiple states until measured. An entangled pair of photons doesn't have definite polarizations until you measure one. At that moment, both polarizations become fixed, even though the photons might be light years apart. The measurement doesn't reveal pre-existing properties, it creates them. And somehow, the other particle knows. This is where language fails. We describe entanglement using words like know and communicate. But particles don't think or send signals. What's happening is more fundamental, woven into the structure of reality itself. Entangled particles aren't separate objects. They're a single quantum system, and measuring part of it affects the whole, regardless of how the parts are distributed in space. Have you ever felt connected to someone far away, as if you knew what they were feeling without a word exchanged? Entanglement is nothing like that. Of course, but the metaphor hints at why it captivates us. It suggests the universe has threads we can't see linking things in ways that defy our everyday experience. By the early 2000s, entanglement moved from theoretical curiosity to practical technology. Quantum cryptography uses entangled photons to create unbreakable codes. If someone tries to intercept the photons, the entanglement breaks and the eavesdropping is detected. China launched the Michis satellite in 2016, which successfully distributed entangled photons between ground stations over 1,000 kilometers apart. The experiment confirmed that entanglement persists even through the vacuum of space across distances where light takes milliseconds to travel. Quantum computing relies on entanglement too. Classical computers process bits ones and zeros. Quantum computers use qubits, which can be both 1 and 0 simultaneously thanks to superposition. But the real power comes when qubits become entangled. An entangled system of qubits can represent an exponentially larger set of possibilities than isolated qubits. It's this entanglement that allows quantum computers to solve certain problems, like factoring large numbers or simulating molecular interactions, far faster than any classical machine. But building stable entangled systems is extraordinarily difficult. Entanglement is fragile. Interact with the environment, heat-light vibrations, and the entanglement collapses a process called decoherence. Quantum computers must be isolated, cooled to near absolute zero, shielded from interference. Even then, maintaining entanglement for more than a few seconds is a triumph. Researchers are also exploring quantum teleportation, which sounds like science fiction, but is experimentally verified. Quantum teleportation doesn't move matter. It transfers the quantum state of one particle to another using entanglement. You start with two entangled particles. You perform a measurement on one particle and the particle you want to teleport. The measurement destroys the original state, but allows you to reconstruct it on the distant entangled particle using the measurement results. The information about the quantum state is transmitted, but the transmission still requires classical communication, sending the measurement results at light speed or slower, so you're not violating relativity. You're exploiting entanglement as a resource. In 2017, Chinese scientists used the Michia satellite to teleport a quantum state from the ground to orbit a distance of over 1,400 kilometers. It worked. The quantum state was destroyed on Earth and reconstructed in space, mediated by entangled photons. This isn't teleporting people or objects, but it's a proof of principle, a glimpse of technologies that might one day enable quantum networks spanning continents or planets. Still, the philosophical questions linger. What does entanglement mean for the nature of reality? If particles don't have definite properties until measured, and measuring one affects another instantly, across space, does that imply the universe is fundamentally non-local? That there's no here and there at the quantum level, only interconnected systems? Some interpretations of quantum mechanics embrace this. The many worlds interpretation suggests that every quantum measurement splits reality into branches, and entanglement links states across those branches. The pilot wave theory proposes that particles are guided by an underlying wave that extends through space, connecting entangled particles through this hidden field. Each interpretation tries to make sense of the same experimental results, but they paint very different pictures of reality. Most physicists take a pragmatic view. Entanglement is a tool, a phenomenon we can predict and use even if its deeper meaning remains elusive. Richard Feynman famously said, "I think I can safely say that nobody understands quantum mechanics." He wasn't admitting defeat. He was acknowledging humility. The math works. The predictions match experiments. But understanding, really grasping what it means, might be beyond our intuitive reach. There's a common misconception that entanglement allows telepathy or faster-than-light travel. Science fiction loves this idea, but the reality is more constrained. Entanglement correlates measurements. It doesn't let you choose what you measure or send signals. The randomness is baked in. You can see patterns in the correlations after comparing notes with your distant partner, but you can encode messages in those patterns. The universe protects causality. Yet within those constraints, entanglement does something extraordinary. It demonstrates that the universe is more interconnected than classical physics ever imagined. Two particles created together and then separated by any distance retain a bond that defies locality. Not in a mystical sense, but in a precise mathematical, experimentally verified sense. The bond is real. Researchers have entangled not just photons, but atoms, ions, even tiny diamonds. In 2011, scientists entangled two macroscopic diamond crystals, each containing trillions of atoms, separated by 15 centimeters. It's still microscopic by everyday standards, but it pushes entanglement closer to the scale of objects we can see and touch. Could larger objects become entangled? Could you in principle entangle two baseballs? The physics doesn't forbid it, but the practical challenges are immense. The larger the object, the more it interacts with the environment, and the faster decoherence destroys entanglement. There's also speculation about biological systems. Some researchers suggest that quantum effects, including entanglement, might play a role in photosynthesis, bird navigation, even consciousness. These ideas are controversial and far from proven. Most biological processes operate at temperatures and timescales where quantum coherence should collapse instantly. But nature is full of surprises, and if biology has found ways to exploit quantum mechanics, it would rewrite our understanding of life itself. For now, entanglement remains a phenomenon mostly confined to laboratories and carefully controlled experiments, but its implications ripple outward. It challenges our notions of separateness. In classical physics, objects are distinct, independent. In quantum mechanics, once particles interact, they can become parts of a unified whole, and that unity persists even when the particles drift apart. Separation becomes an illusion, or at least an incomplete description. Einstein wanted a universe that was local and deterministic, where objects have definite properties, causes precede effects, and nothing acts at a distance without mediation. Quantum mechanics offers something else, a universe where properties emerge from measurement, where correlations span space instantly, where the act of observation shapes reality. And here we are, a century after the quantum revolution began, still grappling with its meaning. Entanglement works. We use it in technology. We test it in experiments. We've closed loopholes, ruled out alternatives, confirmed it beyond reasonable doubt. But we don't fully understand why the universe permits such connections or what they reveal about the fabric of reality. Maybe that's fitting. The universe doesn't owe us comprehensibility. It presents phenomena, and we do our best to model them, predict them, harness them. Entanglement is one of those gifts, strange, powerful, humbling, a reminder that the deeper we look, the more the cosmos defies our intuitions. So, we keep probing, keep experimenting, keep asking what it means for two particles to share a state across the void. And in their silent, instantaneous correlation, we glimpse something profound, that connection at the quantum level transcends distance, that the universe, however vast, is threaded with invisible bonds. That separateness might be less fundamental than we thought. Einstein called it spooky. He meant it as criticism. But maybe spooky is just another word for wondrous, for phenomena that stretch our understanding and invite us to see reality, not as we wish it were, but as it truly is, strange, interconnected, and far more interesting than common sense would suggest. And if space can bend in ways that link particles across galaxies, it can also bend in ways that twist something even more fundamental, something we take for granted every single day. What if I told you that right now, at this very moment, time is moving at different speeds depending on where you are? That a clock on the first floor of a building ticks slower than one on the 10th floor? That astronauts age slightly less than people on Earth? That near certain objects in space-time doesn't just slow, it nearly stops. This isn't philosophy, it's physics. And it's been measured, tested, and confirmed thousands of times. In 1905, Albert Einstein published his theory of special relativity. It was revolutionary, but it dealt only with objects moving at constant speeds. 10 years later, in 1915, he completed general relativity, a theory that included gravity. And what Einstein discovered changed everything we thought we knew about time. General relativity revealed that gravity isn't a force in the traditional sense. It's a curvature of space-time. Massive objects, planets, stars, black holes bend the fabric of space and time around them like a bowling ball placed on a stretched rubber sheet. Objects moving near that curvature follow curved paths which we perceive as gravitational attraction. But here's the strange part. When space-time curves, time itself changes speed. The stronger the gravitational field, the slower time moves. This is called gravitational time dilation. And it means that clocks run at different rates depending on how deep they are in a gravitational well. A clock at sea level ticks slower than one on a mountaintop. The difference is tiny nanoseconds per day, but it's real. And when you approach objects with extreme gravity, the effect becomes dramatic. Consider a black hole, not the supermassive giants lurking at the centers of galaxies, but a stellar mass black hole, the remnant of a massive star that collapsed under its own gravity. The boundary around a black hole, where escape velocity equals the speed of light, is called the event horizon. Cross it, and you can never return. Light itself cannot escape. But even before you reach that point, time begins to behave strangely. Imagine two astronauts. One stays on a spaceship far from the black hole. The other descends toward the event horizon in a smaller pod. As the descending astronaut gets closer, time for them slows relative to the astronaut watching from safety. If the distant astronaut could see their companion's clock, it would appear to tick slower and slower. At the event horizon, it would appear to stop entirely. The descending astronaut, however, wouldn't notice anything unusual about their own time. Their clock would tick normally from their perspective. It's only relative to the outside universe that time has slowed. This isn't speculation. It's a direct consequence of Einstein's equations, and we've tested analogous effects in less extreme environments. In 1971, physicists Joseph Hafele and Richard Keating conducted an experiment. They took 4 cesium atomic clocks, incredibly precise timekeepers, and flew them around the world on commercial airplanes. 2 flew eastward, 2 westward. When the clocks returned, they were compared to reference clocks that had remained on the ground. The results matched Einstein's predictions. The clocks that flew eastward moving faster relative to Earth's surface due to the planet's rotation had lost time about 59 nanoseconds. The clocks that flew westward moving slower relative to the surface had gained time about 273 nanoseconds. The differences were tiny but measurable. Time had literally passed at different rates for the clocks in motion and at different altitudes. GPS satellites experience this effect constantly. They orbit about 20,000 kilometers above Earth, where gravity is weaker than at the surface. According to general relativity, time moves faster for the satellites than for us on the ground, about 45 microseconds per day faster. But the satellites are also moving at high speeds, which according to special relativity makes their clocks run slower by about 7 microseconds per day. Combine both effects, and the satellite's clocks gain about 38 microseconds per day compared to ground-based clocks. That might not sound like much, but GPS relies on precise timing. Signals from satellites travel at the speed of light, and the system calculates your position based on how long those signals take to reach you. A timing error of 38 microseconds translates to a position error of about 11 kilometers. Without correcting for relativity, GPS would be useless. Every navigation device in your car, every map on your phone works because engineers account for time dilation. Relativity isn't abstract. It's embedded in the technology we use daily. But near black holes, the effects are far more extreme. In 2014, the film Interstellar depicted astronauts landing on a planet orbiting close to a supermassive black hole called Gargantua. The planet's proximity to the black hole meant that time there moved much slower than in the rest of the universe. The astronauts spent a few hours on the surface, but when they returned to their ship, over 20 years had passed for their crewmate who stayed behind. The filmmakers worked with physicist Kip Thorne to ensure the depiction was scientifically accurate. And it was. For a planet orbiting that, close to a black hole without falling in the time dilation ratio shown in the film, 1 hour equals 7 years, is plausible. The planet would need to be orbiting at nearly the speed of light, experiencing extreme gravitational effects. But the math holds. It's an extreme scenario, but not an impossible one. Think about what that means. If you could survive near a black hole's event horizon and then return to the wider universe, you'd emerge into a future you never lived. Your family would have aged, your friends would be gone, civilizations could rise and fall while you experienced mere moments. You'd be a time traveler moving only forward, unable to reverse the journey. Black holes take time dilation to its limit. At the event horizon, time, from an outside perspective, stops completely. A falling object would appear frozen, never quite reaching the boundary, its light redshifted into invisibility. But, from the object's own perspective, time continues. It crosses the horizon without pause, doomed to reach the singularity at the center, where space-time curvature becomes infinite and our equations break down. This creates paradoxes. If you watch someone fall into a black hole, you'd never see them cross the event horizon. They'd slow redden fade, but never disappear. Yet from their perspective, they'd cross in finite time and be destroyed. Both perspectives are correct within their own frames of reference. Time, it turns out, isn't universal. It's local, dependent on where you are and how you're moving. Physicists discovered another strange implication in the 1970s. Stephen Hawking showed that black holes aren't entirely black. Quantum effects near the event horizon allow them to emit radiation now called Hawking radiation. Over unimaginable timescales, black holes evaporate, losing mass until they vanish entirely. But here's where time dilation enters. An outside observer would never see the black hole fully evaporate because time near the horizon slows infinitely. The process would take longer than the current age of the universe. Yet, for a particle near the event horizon, the black hole's lifetime is finite. Have you ever felt like time passed differently in different situations? Waiting feels long, excitement feels short, but that's perception psychology. What we're discussing is objective measurable variation in time itself. Clocks don't just seem to tick at different rates, they do tick at different rates, and the universe doesn't care about our intuitions. Neutron stars, though, not black holes, also warp time significantly. These are the collapsed cores of massive stars, so dense that a sugar cube-sized piece weighs as much as all of humanity. Their gravity is immense. A clock on a neutron star's surface would run about 30% slower than a clock far from any massive object. If you could stand on a neutron star, though the gravity would crush you instantly, time for you would crawl compared to the rest of the universe. Researchers propose another consequence of extreme time dilation, the so-called frozen star hypothesis. When stars collapse to form black holes, the process appears to halt from an external viewpoint. The star's surface never quite crosses its own event horizon due to infinite time dilation. From the star's perspective, it collapses in finite time, but to the universe, it's frozen mid-collapse. Some physicists argue this means black holes as we understand them might not fully form within the observable universe's lifetime. It's a controversial idea, challenging conventional black hole physics, but it highlights how deeply time dilation affects even the existence of objects. Time dilation also intersects with the speed of light. Nothing with mass can reach light speed, because doing so would require infinite energy. But there's another reason time dilation. As you accelerate closer to light speed, time for you slows relative to the outside world. At light speed, time would stop entirely. Photons, particles of light, experience no passage of time. From a photon's perspective, it's created and absorbed in the same instant, even if it travels billions of light years. The universe is timeless for light itself. The twin paradox illustrates this. Imagine twins. One stays on Earth. The other travels at near light speed to a distant star and returns. When they reunite, the traveling twin is younger. Time passed slower for them due to their velocity. This isn't symmetrical. Both twins don't age equally. The one who accelerated and decelerated experiences less time. Experiments with particles confirm this. Muons created in Earth's atmosphere decay in microseconds, but moving at near light speed, they last longer from our perspective, reaching the ground before decaying. Time dilation extends their lives. Philosophers sometimes ask if time can slow stop or vary. Is it real? Physicists answer yes, but not in the way we assumed. Time isn't a universal river carrying everything forward at the same rate. It's flexible, intertwined with space, shaped by mass and motion. The flow of time is local personal, dependent on your path through space-time. General relativity also predicts frame dragging, where rotating massive objects twist space-time around them, dragging nearby objects along. Earth does this to a tiny extent. Satellites in orbit experience slight shifts in their trajectories due to Earth's rotation pulling space-time. Near a rotating black hole, the effect is extreme. Close enough space-time itself rotates so fiercely that standing still becomes impossible. You'd be dragged into orbit whether you wanted to or not. This region is called the ergosphere, and within it, time and space swap roles partially. The geometry is so warped that future and past lose their usual meanings. Black hole collisions reveal time dilation on cosmic scales. When two black holes spiral together, they warp space-time, violently emitting gravitational waves, ripples that propagate through the fabric of the universe. The LIGO and Virgo detectors have measured these waves, confirming another of Einstein's predictions. In the final moments before merger, the black holes orbit each other at significant fractions of light speed, and time dilation affects how we observe the event. The gravitational waves themselves carry information about the extreme space-time curvature, including time dilation effects. We sometimes imagine time as a dimension like space, but it's not symmetrical. You can move forward or backward in space, but time has a direction. Entropy increases, cause precedes effect. Yet near black holes, even this breaks down. Inside the event horizon, all paths lead inward. Time becomes spatial. In a sense, you can no more avoid reaching the singularity than you can avoid moving forward through time normally. The future is not ahead of you. It's below you at the center. Some solutions to Einstein's equations suggest closed time-like curves, paths through space-time that loop back on themselves, potentially allowing time travel. Rotating black holes might permit this in theory, though whether such solutions represent physical reality is debated. Most physicists suspect quantum mechanics or other factors prevent actual time travel, preserving causality. But the equations leave the door open just a crack. Time dilation also impacts cosmology. Light from distant galaxies is redshifted, stretched by the universe's expansion. But when that light passes near massive objects like galaxy clusters, gravitational lensing occurs, and time dilation affects how we perceive events in those distant regions. Supernovae and lensed galaxies appear to unfold more slowly. From our perspective, they're light curves stretched by the warping of space-time along the path to Earth. The practical implications extend beyond GPS. Future interstellar travel, if it ever becomes possible, would involve time dilation. A spaceship traveling at relativistic speeds would allow astronauts to cover vast distances within their lifetimes, even if centuries pass on Earth. They'd return to a world transformed, perhaps unrecognizable. It's a one-way journey into the future, and it raises profound questions about connection, identity, continuity. Einstein gave us a universe where time is negotiable, where seconds and centuries depend on where you stand and how you move. It's disorienting, uncomfortable even, but it's also wondrous. Time isn't a rigid framework imposed on reality. It's part of reality, woven into the fabric of existence, shaped by matter and energy. So, when you check your watch, remember it's not measuring an absolute universal time. It's measuring your personal journey through space-time, influenced by gravity, motion, and the curvature of the cosmos. Every tick is local, every second relative. And somewhere out there near the event horizon of a black hole, time has slowed to a crawl. Photons orbit in endless loops, matter spirals inward, stretched and torn. And the universe patient and indifferent watches as clocks forget to tick, and time itself bends under the weight of gravity. We've journeyed through silence, invisibility signals, visitors, ancient light, quantum strangeness, and now the flexibility of time itself. But every mystery we've explored shares something in common, a reminder of how much remains unknown, how deeply the cosmos resists easy answers. We've traveled far tonight, through silence that stretches across galaxies, through invisible matter holding the cosmos together, through signals that flash once and vanish, through visitors that pass without stopping, through ancient light carrying flaws in creation's first photograph, through quantum connections that ignore distance, through time itself bending and slowing near the universe's darkest objects. 8 mysteries, 8 invitations to wonder, and if you're waiting for me to tie them all together with a neat conclusion to reveal the hidden answer that explains everything I can't. Because that's not how the universe works. Science isn't a collection of facts we've memorized and filed away. It's an ongoing conversation with reality, and reality keeps changing the subject. Every answer we find opens 3 new questions. Every mystery we solve reveals deeper mysteries waiting beneath. And somehow, that's more beautiful than certainty ever could be. Think about what we've learned just in the last century. In 1920, we thought the Milky Way was the entire universe. Then Edwin Hubble showed us galaxies beyond counting, rushing away from each other, expanding into a cosmos larger than anyone imagined. In the 1960s, we discovered the cosmic microwave background proof that the universe had a beginning, a moment of creation we could measure and map. In the 1990s, we found that the universe isn't just expanding, it's accelerating, driven by a dark energy we can't explain. Each discovery didn't complete the picture. It expanded the canvas, showed us how much more there was to paint. The Fermi paradox asks where everyone is, and we still don't know. Maybe we're alone, maybe we're early. Maybe civilizations rise and fall too quickly to overlap in this vast cosmic timeline. Or maybe they're out there watching, waiting silent for reasons we can't fathom. The question remains unanswered, but asking it has taught us something profound. Intelligence, wherever it arises, is rare enough to be precious. Consciousness, the ability to look at the stars and wonder, might be the universe's rarest gift. Dark matter holds galaxies together, yet we've never touched it, never seen it directly. We know it's there the way you know someone's in a room because the door is open, the lights are on, the air feels occupied. We map its influence, trace its effects, build detectors hoping for a whisper of interaction. Decades of searching have yielded tantalizing hints, but no definitive answers. And that persistence, that willingness to keep looking even when the universe stays silent, that's science at its most human. Fast radio bursts shout across billions of light years, and we're only beginning to understand what makes them. Magnetars, maybe. Colliding stars, perhaps. Something else entirely. Each new detection refines our theories, narrows the possibilities. But the universe is vast, and phenomena we've never imagined might be unfolding in corners we haven't looked yet. The sky still has secrets. The WOW signal and Oumuamua came and went, leaving us with fragments, a 72-second transmission, a few weeks of observation, incomplete data, unanswered questions. And maybe that's fitting. Maybe the universe doesn't hand us complete stories. It offers glimpses, and we have to fill in the rest, with patience, with better instruments, with the humility to admit when we don't know. The cosmic microwave background shows us the universe's infancy, but even that ancient light carries anomalies we can't explain. The cold spot, the axis of evil, features that shouldn't exist according to our models, yet persist in every observation. They're not mistakes. They're not going away. They're the universe telling us quietly but insistently that our understanding is incomplete, that the story we've told ourselves about creation, however elegant, might need revision. Quantum entanglement defied Einstein's intuition, and he was one of the greatest minds in history. Particles remain connected across distances that should sever any bond correlating their properties instantly in ways that don't transmit information but do transcend locality. It works. We use it. We build technology around it. But what it means, what it reveals about the nature of reality, still sparks debate. Maybe the universe is fundamentally non-local. Maybe separateness is an illusion. Or maybe our language just isn't equipped to describe what's really happening. And time, which we experience as constant unidirectional universal bends, slows, stops, changes speed depending on where you are and how you're moving. Astronauts age slower. Clocks on mountains tick faster than clocks in valleys. Near black holes, time stretches so dramatically that hours become years, and the boundary between past and future blurs. Einstein gave us equations that predict this, and every test confirms them. But understanding it, truly grasping what it means for time to be flexible, remains elusive. Do you see the pattern? Every mystery we've explored tonight shares a common thread. The universe is stranger than we thought, deeper, more layered, more resistant to simple explanations. And that strangeness isn't a failure of science, it's a feature. It's the universe being exactly what it is, a place too complex, too vast, too fundamentally weird to be fully captured by any single theory or perspective. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." He was right. But here's the thing. He also understood the waiting isn't passive, it's active. It requires building telescopes, launching satellites, conducting experiments, analyzing data, proposing theories, testing them, revising them, starting over when they fail. It requires a kind of stubborn curiosity that refuses to be satisfied with mystery, even while acknowledging that mystery might be all we ever get. Science doesn't diminish wonder, it amplifies it. Before we understood stellar nucleosynthesis, stars were just lights in the sky. Now we know they're forges where hydrogen fuses into helium, helium into carbon, into oxygen, all the way up the periodic table until iron. We know that when massive stars explode, they scatter these elements into space, seeding the cosmos with the raw materials for planets, for life, for us. Every atom in your body was forged in a star that died billions of years ago. You are quite literally made of stardust. Does knowing that make stars less beautiful, or does it make them more wondrous, more connected to you, more meaningful? The same is true for mysteries. Knowing the dark matter exists, even if we can't see it, makes the universe more intricate. Knowing that signals flash across the cosmos, with energy beyond comprehension, makes space feel more alive. Knowing that time itself is negotiable makes every second you experience feel more precious, more localized, more yours. And the mysteries we haven't solved yet, they're not failures, they're frontiers. Every unanswered question is a space where the next generation of scientists will make their mark. Every anomaly is an opportunity. Every gap in our knowledge is an invitation to explore. So, what do we do with mystery? We sit with it, we let it be uncomfortable, we resist the urge to fill gaps with guesses to pretend we know more than we do. And then, we get to work. We design better experiments, we build better instruments. We collaborate, argue, test, refine. We fail more often than we succeed, but we keep trying because that's what curiosity demands. The universe doesn't owe us answers. It doesn't arrange itself for our convenience or comprehension. It simply is vast, ancient, and different to our need for closure. But here's the miracle: we care anyway. We look up at the night sky, at stars whose light left them before we were born, and we ask why. We build machines to listen for signals we may never hear. We search for particles that might not exist. We map the invisible measure, the unmeasurable imagine the unimaginable. And in that effort, in that restless need to understand, we find meaning. Not in the answers, though. Answers are wonderful when they come, but in the asking, in the pursuit, in the quiet thrill of not knowing paired with the stubborn hope that maybe we'll figure it out. Tonight we've walked through some of the cosmos's deepest riddles. We haven't solved them. We've only acknowledged their existence, appreciated their depth, felt the weight of how much remains unknown. And if that leaves you feeling small, good. You should feel small. The universe is incomprehensibly large, and we are tiny fragments of matter briefly organized into consciousness. But if it also leaves you feeling connected to the stars, to the questions to everyone else who's ever looked up and wondered, then you've felt what science offers at its best. Not dominion over nature, but kinship with it. Not answers that close doors, but questions that open them wider. The Fermi paradox reminds us we might be alone, and that possibility makes every voice, every mind, every moment of awareness precious. Dark matter reminds us that most of reality is invisible, and that humility is the beginning of wisdom. Fast radio bursts remind us the universe still has surprises, still shouts when we least expect it. Oumuamua and the Wow signal remind us that visitors and messages might come once and never again, and we have to be ready. The cosmic microwave background reminds us that even the oldest light carries secrets. Quantum entanglement reminds us that connection transcends distance. And time dilation reminds us that every second is a gift, shaped by where we are and how we move through this strange curved space-time we call home. We are the universe's way of knowing itself. Atoms arranged just so briefly aware, capable of asking why. And in the time we have, whether measured in years or in the relative flow near a black hole's edge, we get to explore, to question, to marvel. So, sleep well tonight knowing that the mysteries are still out there, that the universe hasn't run out of puzzles, that tomorrow's scientists will find answers we can't imagine, and those answers will raise questions we haven't thought to ask. The cosmos whispers in riddles, and we, fragile and curious, keep listening. Thank you for drifting through these mysteries with me tonight, for letting wonder be enough, for embracing the beauty of not knowing while still reaching for understanding. If you found something here that resonated, a question that lingered, a perspective that shifted, then this quiet journey was worth taking. There are more stories waiting in the night sky, more phenomena that defy explanation, more corners of reality that resist our models, more invitations to explore. And when you're ready, we'll wander through them together. Until then, rest easy. Dream of stars and silence of particles that remember each other across the void of time, bending under gravity's patient hand. The universe is still speaking, and we'll keep listening. Good night,